Well, now the idea is that these x sub n's form a Cauchy sequence. We will first show that. Well, since the space is complete, that will converge to something. But since this is a sequence, the sequence of x sub n's, it's a sequence in cap k, which is closed. So the limit will belong to cap k. But since script g is an open covering for cap k, well, that will belong to some open set in that collection, and that will yield a contradiction with that each of the b sub k's was such that script g had no finite subcovering for the intersection of b sub k with cap k. So the rest of the proof will consist of those steps. So let us start then first by showing that the sequence of x sub n's is a Cauchy sequence. So we first need an estimation concerning the distance between two consecutive terms. So for that, take any n in n. Well, what we know is Bn and Bn minus 1, that will have a non-empty intersection. So we can pick something from there and then have an estimation concerning the distance between x sub n minus 1 and x sub n using the triangle inequality via x in the intersection. Now, Bn minus 1 intersection Bn is non-empty. Pick some x in that intersection. Now, rho of xn minus 1, xn, that's less than or equal to rho xn minus 1x plus rho x xn. But x is in Bn minus 1, so the distance between these is m less than m over 2 to the power n minus 1, because this was the radius of the n minus first ball. But x is in Bn as well, so here we'll have m over 2 to the power n. Now this will be 3m over 2 to the power n. Well, I can keep this as it is, but I can simplify it as well, because the only thing which will matter is that this quantity will tend to 0 as n tends to infinity. So, well, I can replace this by 4m divided by 2 to the power n, but that's just m over 2 to the power n minus 2, which again will converge to 0 as n tends to infinity. But in order to show that the sequence in question is Cauchy, well, the distance between two consecutive terms, that's fine, but I need to have an estimation about the distance between any two terms of the sequence beyond some point n. So now let PQ be in n with, well, one will be larger, say Q larger than P, larger than or equal to n. I have taken some place in the sequence and have taken 2 points beyond that. Now, rho xp, xq. Well, no matter how far apart from each other these are, well, I can use the triangle inequality successively, and this will then be, in terms of the distances of 2 consecutive points in the sequence, rho of xp, xp plus 1, plus up to rho of xq minus 1, xq. So this is an upper bound for this in terms of distances between consecutive points. Now this will be less than or equal to m over, according to what I have here, 2p minus 1, then plus m over 2 to the power q minus 2. Now here I have part of a geometric progression, or geometric series, in fact. Well, let's compute what that is. Here I have, let me put S. I can never remember the formula for the sum, but it's, let me forget about m, 2p minus 1 plus 1 over 2 to the power q minus 2. Well, here the multiplier is 1/2. Each time I multiply by 1/2. So 1/2 s, that will be 1 over 2 to the power p minus 2. No. I will multiply this by, this will be p, right? And then here 1 over 2 to the power q minus 1. If I subtract this from the above, I'll get 1/2 s. Now here we'll have 1 over 2 to the power p minus 1. Everything will get cancelled until this 1 over 2 to the power q minus 1. Now I can multiply everything by 2. S will be 1 over 2 to the power p minus 2 minus 1 over 2 to the power q minus 2. So this will be equal to m over 2 to the power p minus 2 minus m over 2 to the power q minus 2. But now, again, as I need something which converges to 0, I can be rough. Well, this will be less than m over 2 to the power p minus 2. I can forget about the term which I subtract, but p is larger than or equal to n, so this will be less than or equal to m over 2 to the power n minus 2. This estimation now will easily allow me to show that xn is a Cauchy sequence. Now let any epsilon greater than 0 be given. Well, the only thing is I will take n so large that this will become less than epsilon. Now, there is some k in n such that m over 2 to the power k minus 2, that will be less than epsilon. Now for any PQ in N with P and Q larger than or equal to K. Well, here we took Q larger than P, but if P and Q are the same, this will zero, and trivially the same inequality will be satisfied. We have rho xm, no, x, I said pq, xp, xq, that will be less than or equal to m over, here this will be replaced by cap k, 2 to the power k minus 2, but that's less than epsilon. So xn is a Cauchy sequence in our metric space X rho. Now, since X rho is complete, xn converges to A for some A in X. But what else do we know about xn? It's a sequence in cap k, and cap k is closed, so A belongs to k. As xn is a sequence in k, and k is closed, we have A is in cap k. Now, that takes us to the next item on our agenda. We are very close to getting a contradiction. Well, script G, that's an open covering of K. A is in K, so script G contains a member, an open set, which contains lowercase a. Now, as script G is an open covering of K, there is some, say, G naught in script G with A is in G naught. The condition which we wish to get a contradiction with is that for each cap B sub n in the sequence, the condition was that script G has no finite subcovering for the intersection of Bn. No matter how large n is, script G has no finite subcovering for the intersection of Bn with cap k. Okay? Well, to get that contradiction, what do we know? We know two things. One is that xn converges to A, and the other is, well, the radii of the balls in the sequence, they converge to 0. Now, we're in a metric space. This is an open set. Well, then there must be some delta ball about A, which is entirely contained in here. Now, B rho delta A, that will be contained in G0 for some delta positive. Now, we have two convergences, and we have delta let's have half of delta for one convergence and the other half for the other convergence. Since x sub n converges to A, there is some k1 in n such that for all n larger than or equal to k1, we have rho xn a less than delta over 2. Well, next, also, there is some k2 in n such that for all n larger than or equal to k2, the radius of the nth ball, m over 2 to the power n, that will be less than delta over 2. Well, I wish to be in a domain where both of these hold, so let me just take the maximum of k1 and k2. Set k equal to the maximum of k1 and k2. Now let us take cap b sub k. We have actually cooked up the entire thing in such a way that cap b sub k will be entirely contained in G0. But that will yield the desired contradiction. Because if cap b sub k is in here, then cap p sub k intersection cap k is in here, but then singleton G0, that's a very finite subcovering of script G for that intersection, contradicting the construction of the sequence. Okay, let's do that. Take any x in b sub k. Well, we wish to show that x is in G0, but now we have it done in such a way that we can show that x is in this delta ball about A. Well, to show that, let us consider the distance between x sub k, that's the center of this, and A. But now that will be less than or equal to, I'm sorry, between x and A. Okay, I want to show that this is less than delta, but this now will be less than x sub k plus rho of x sub k A. Now, what do we know about this x sub k? Well, x is in bk. bk is the m over 2 to the power k ball about x sub k. So this is less than m over 2 to the power k. But k is larger than or equal to k2, so this is less than delta over 2. Well, k is larger than or equal to k1 as well, then this distance is less than delta over 2. Now this comes from the diameter of bk, And this comes from the convergence of the sequence xn to a, but then this is less than delta. So x is in the delta ball about a, but that's in G naught. So bk, that's contained in G naught because any point in bk is a point of G naught. So G naught is a finite subcovering of script G for bk intersection k, a contradiction. Well, we reached this contradiction starting from the supposition that K was not compact, so that supposition must be false. Thus, K is compact. Completing the proof of this. Okay? So, this is useful. Most of the spaces that you will deal with in economic theory, be it in macro or micro, well, they will be complete spaces. So, well, then this might be useful in that regard. Now, we will close this section by just giving an example. Well, I will send the details in written form by email either today or tomorrow, that completeness is unfortunately not a topological concept. In the sense that you can have on one and the same set two different metrics which induce the same topology, thus they are equivalent, but it might be the space might be complete with respect to one of the two metrics, but not so with respect to the other. Any questions about the proof of this? Well, at this point, well, there is no problem if you have some problem, some technical problem with some of the parts, subsections of the proof. But the crucial point is that you have the structure itself, okay? So you will first construct a sequence which is Cauchy. Well, then you find its limit, but that limit will be in cap K. Well, then, using the fact that the sets in the sequence, the radii, they converge to nil, well, you find something, some ball whose intersection with K admits a finite subcovering for K. So, but then I advise you to go through the details of each subsection. But now let's come to the example. Well, there are, of course, various examples, but here we take this on R. Well, one of the metrics we'll consider is D, the usual metric. The other will be this. For each xy in R, define m of xy equal to, we'll take this distance, Now first, we'll show that M is a metric on R. Second, D is the usual metric. M and D are equivalent on R, so they induce the same topology. Thirdly, you take the sequence N, that is the sequence of natural numbers, 1, 2, 3, and so on. This turns out to be a Cauchy sequence in Rn. But not in Rd. And fourth, N is not convergent with respect to M. So here you have a Cauchy sequence which is not convergent. But then Rm is not complete while Rd is so. Okay, so I will send you a document which contains the proofs of each item in here. Well, if you have any problems, we can discuss that back in class as well. But let's not lose time doing that. That'll take too much time. Okay? Okay, so that closes our first chapter, which was about elementary topological properties of Euclidean spaces. And concerning, well, what are the climaxes? Well, one is if you have a real valued function which is continuous and whose domain is compact in some topological space, then the function attains both its maximum and minimum. Moreover, the set of maximizers as well as the set of minimizers, well, they are compact subsets of the domain. Well, so knowing what's compact and knowing what's continuous, that's crucial, because if you wish to use that theorem, then you have to be able to distinguish between compact, non-compact, continuous, discontinuous, not continuous. And this last thing says, well, we have an easy way of determining whether a given set is compact or not if the space is complete. Okay? But that's only about the existence and the structure of the set of maximizers or minimizers. How to find them? Well, then we need differentiation. So that will be our next chapter. But what